useful, especially in a difficult discussion, right, where people have strong feelings on either side of the particular issue, to try to identify which is which. Both are necessary, both can be controversial, and for the next couple hours or so on the sort of basic energy science, we're going to be really intending to cover more of the facts analysis. That's not to say that where sometimes the more fun and interesting discussions will not occur. In fact, they will be occurring through the next 3 weeks. Okay, so with this in mind, let's just start off getting everybody sort of thinking, participating a little bit. Let's do a factual versus ethical assertion question and see if we can agree on some various things I'm going to say and see if there's a consensus from all of you as to which side, what type of question this might be or statement. So here's a statement. Global fossil fuel burning emits 34 billion tons of carbon dioxide equivalent per year. Which do you think? Is this a factual assertion that could be sort of proven, or is it more of an ethical assertion? Factual? Okay, I would agree. Factual assertion. Here's another one. If CO2 concentrations are doubled, then average temperatures will increase by some range, 1.5 to 5.8 degrees Celsius in the next 100 years. How many think it's factual? And how many think it's ethical? Okay, so we think at least this is a factual type question that can be answered in terms of science and measurements and reasonable models. How about this one? No one has the right to follow the air of his breed. How many think that's factual? Ethical. I would agree. How about this one? A complete melting of the Greenland ice cap would cause a 7 meters sea level rise. How many say factual? Factual, any ethical? Okay. And how about this one? Developed countries get most of the carbon dioxide up in the atmosphere, therefore they should clean it up. Yeah, factual?
Unethical.
Ethical? Unethical? How about this one? No country will emit more carbon dioxide in the next decade than the developing countries, therefore they should clean it up. Factual, ethical, or unethical? So this is something that may be useful to think about as it goes forward. All right, with that little introduction, you will also start to hear about policy assertions in SISE. Right? For example, what the U.S. ought to do, ought to produce 20% electricity by wind and solar. We ought to replace gasoline vehicles with electric. We should or should not cut carbon emissions. So these are questions about what is good for the country, which we all have a stake in, which you will also be discussing in the next few weeks. All right, so with that, let's now move back sort of in the first camp of just setting a foundation so we're all talking and starting from the same place in terms of at least some of the science. And I want to talk a little bit about energy, power, and the second law of thermodynamics. So, without further ado, here we go. I need 6 volunteers, because I don't want this to be me talking, and I want you to all get used to talking, to just read 6 statements I'm going to show one after the other. So just to help me out, I'm going to try to maybe go sort of around clockwise from here. So is there like a volunteer here who would just raise your hand? Anyone? Okay, volunteer 1, 2, 3. Maybe over here. 4, 5, 6. Okay, all of you remember sort of who I pointed at. I'm just going to go right around. All I'm going to do is ask you to read the statements as they show up. So what statements are they? Well, there's a book written already 20 years ago, right, by Vaclav, Smil, called Energy and World History. And so first line here, go.
In contrast to the slow, cumulative transformations of traditional societies, fossil fuel-based industrialization has brought about almost instantaneous socioeconomic changes.
Thank you. Next.
The substitution of fossil fuels for biomass and the later replacement of animate energy by electricity and internal combustion engines created a new world within just a few generations.
And next.
The American experience was an extreme example of these compressed changes.
And next.
More than in any other modern nation, the United States has acquired its power and influence largely through its extraordinarily high use of energy.
Next.
In the 1850s, the country was an overwhelmingly rural, wood-fueled society of marginal global impact.
And the last.
A century later, after more than tripling its per capita consumption of useful energy and becoming the world's largest producer and consumer of fossil fuels, it was both an economic and military superpower.
Okay, so any general thoughts about this? Do all of you sort of agree with Vaclav Smil in his analysis of his statement 20 years ago? See some nods of head. What about 30 years from now? If you were going to write an updated book for this 30 years from now, would you be talking about the U.S. then, or are there some other countries that might be falling under the same model? Any thoughts? China, India. And in fact, that may even be faster. It took, it took US 100 years, and that may be 50 years only, for example. And so this sort of statement, right, from 20 years ago and 30 years from now will likely be revised in a very significant way for big, huge portions of the world. All right, so let's now, because this is all about energy and what is energy, let's do a little bit of talk from the physics perspective or the historical perspective of energy. So let's set sort of the foundations here for what do we mean when we mean energy. And I think we all may mean somewhat different things. Historically, it derives from this Greek word energia. The 4th century BC, it was typically attributed to Aristotle as sort of, to Aristotle and the statements of happiness as a way of being in action. So I'm happy. You're happy here because we're in action, right? So there's energy there, and maybe there's hints of that in terms of the physics that still hangs around today, as we'll see. Quite a while later, late 1600s, Leibniz, it now started to become much more quantified in terms of its use. Right? The living force, vis viva, right? Where Leibniz noticed in many mechanical systems that this strange quantity, mass times the speed squared, seemed to stay constant. Little science history is interesting. At the time, this was often viewed to be in opposition to Newton, who said it was mv, mass times velocity, not mass times velocity squared that was considered. It's nice in this case to have both people be right. In the mid-1700s, it became more clearly associated with this quantity of motion and connected through the mass times velocity squared part in terms of the term. And by the mid-1800s, it was really firmly associated with this idea of kinetic energy, energy of motion. As you can see, right? Where's your motion? Velocity squared. And also some new ideas started to pop up. Energy was not just about motion, but about energy stored in different ways. For example, such terms as potential energy. We'll talk about that in a little bit. It was also associated with long-running discussions of thermodynamics, which we'll talk about. Is energy a substance? Is it a physical quantity? What is it? How does it manifest itself? So these are deep questions for the scientists of this time. And by the early 1900s, right, and then we really started firmly theoretically establishing what energy is and that it can change forms and some very interesting properties of energy in the world, such as conservation of energy. Okay, so let's have a little bit of whiteboard discussion here. I'd like to have you think about this. I'm going to raise a screen and things. We're going to talk a little bit about what energy means to you, what does power mean to you, and then maybe some relevant units. What we're going to do energy over here. We're going to do power over here. And I just want to hear your first thoughts. It can be anything, and I'll even maybe start it off in terms of when you hear these terms, what things comes to mind. For me, when I think about this, all right, that's what I think of. Anybody else?
Electricity.
Sorry? I didn't hear it.
Electricity.
Electricity, okay.
Natural gas.
Natural gas.
Sun.
Sun.
Geothermal.
Geothermal.
Renewable.
And I'm sorry, say again?
Renewable sources.
Renewables.
Calories.
MC squared.
Very good. Okay. All right, fantastic. How about power? If you think about power, how is that differentiated in your thinking, or isn't it, or what things come to mind?
Voltage.
Perez, all right?
Generation.
Force or motion.
Rate, amount per time.
Does anybody still think in terms of horsepower? Oh, I'm already so old. All right. So, okay, fantastic. So how about units? If you think about units that are associated with this, what are some units? And I think I'm already going to circle one of them. Any other units that would come to mind if you really had to quantify something? BTUs. Is BTU? Okay. Okay, great. All right, 1 to 10. Fantastic. I love all the interaction. So BTU, what is a BTU? Is it energy or power?
Energy.
BTU. Okay. Joules. Which one is that? Okay.
Pounds of steam.
Pounds.
Pounds. Is that energy or power?
Force.
And it's,
Force.
well, for steam, it's energy.
Connected. Okay. So let's see. It needs to have a different unit. Okay. So let's see. We're going to have pressure in some way. Okay. I think I'm going to put a little. We're going to do a little homework research on that to try to get that exact in units. But I get the idea. How about on the power side? I haven't heard any power units. Watts. All right. Any others? Horsepower. Okay.
Electron volts.
Electron volts. Okay. Energy or power. Okay, so it looks like everybody has things in mind in terms of units, and you also have an idea of what the difference is between energy and power. Does anybody just want to, if you had to quickly explain, what is the difference between energy and power? It's sort of already hidden here. And what is the connection, I should say? Anybody want to give a shot?
Energy is equal to power, yeah.
Everybody agree? Or conversely, of course, power is energy. Okay, fantastic. So we all have, you have good ideas of what both energy and power are. You have ideas of units behind it. Do you have ideas of the scales of units? So for example, in calories, what kind of is a reasonable scale of calories? How do you think about calories? Okay, kilocalories, so that's really food calories. That's the way I think about it too. So let's make this calories be food calories. What is sort of a natural number of food calories you might imagine? 2,000. Good, right? Sort of what we eat in a day. How about joules? Do any of you just carry in your head sort of what a scale of a joule is, or what a connection between a number in joules and an actual action or quantity or something?
Newton meters.
Okay, good. So we have an idea of where it comes from. So Newton meters. I mean, the one I always think of is I connect it to potential energy, and I imagine sort of a book of 1 kilogram, 1 meter high, 3 feet off the ground, and that's about 10 joules, for example. And sometimes having scales of these and getting ideas of the numbers can be very helpful, especially going forward. Some units I have no feeling whatsoever for. BTUs I don't. And so if I'm going to get some number in BTUs, and you may have this happen if you have quantitative discussions coming forward, if you have numbers in units that don't mean anything, well, it may be worthwhile transferring, translating them, converting them to something that does. Just an aside. Okay, fantastic. So let's now, okay, so spend a little bit of time thinking about the energy to run a human. And you already sort of set some of the scale for this. All living things do what? What do we all do? Breathe, okay. So we input and output, all right? We eat and breathe, and output, work and waste. Okay, maybe live and recycle. All right, that'll be the theme here from the SISE side. Right? But there's this circle that we do, right? We take in energy in some way, and we put out something as a result. And as I'm sure all of you know, but sometimes it's nice to hear it again and think about it in a slightly different context. Food energy from carbohydrates, fats, proteins, organic acids, right? They're all released, made available to us during respiration, right? During our breathing. So how much energy do we use? I think somebody already said the number, right? 2,000 calories. Have any of you ever converted this to, so calories per day, 2,000 calories per day, so that's an energy over time, right? So what unit is that now? What type of quantity? Energy over time is power, so I can convert that to watts. Have any of you ever converted your calorie use per day to watts?
It's like 100 watts, I think.
Exactly. So we're basically like a 100-watt light bulb in terms of our power use. Okay, so compared to actually then, if you think about it that way, compared to the energy we use every day, it's actually minuscule. In fact, we use far more energy than we actually consume to live ourselves. So it's an interesting thing to at least have in the back of your mind. And a little aside, do any of you have what percentage goes for brain metabolism for us sitting here thinking? What is it? 17, 70? Okay, I think it's about 20%. But I don't know if you'll feel like more or less depending on where you came from. And the rest just goes for our basic living and all of our body parts. All right, so what is a calorie anyway? Well, let's remind ourselves a little bit. Let's do a tiny bit of chemistry here, dabble a little bit. It is energy stored in the chemistry, the chemical compounds that we eat. Let's do the simplest one, right? Sugar, or glucose. And if you happen to remember this, if not, well, this is the reminder. It's got 3 other little elements in it, carbon, hydrogen, and oxygen. They're mixed up just right to form a single chemical molecule. Here's the simplest one, sugar. Right, 6 carbons, 12 hydrogens, 6 oxygens. And you probably all heard the term carbohydrates or carbs, right? That's where it comes from. Carbohydrates, carbon, right? Hydrates for water, for something dehydrated. And it's just this is a more generalized chemical compound, right? We often write as different numbers of carbons and the hydrogen and the water molecules can combine. Okay, so with this in mind, again, I know you probably all know this, but it's maybe useful to think about this in the context of energy, energy use, and the world we live in. Let's talk about one of nature's many cycles. And it's a very simple circle of life cycle. So here we are, we breathe. What are we breathing in? What is our body wanting from breathing? Why am I breathing? Oxygen, right. Now what form does oxygen float around in the atmosphere? Do you happen to know? Is it just oxygen all by itself, one little molecule, or is it primarily O2? Right, okay, so oxygen. We eat, let's say, only sugar. Okay, that's not so healthy, but if you did, that keeps it simple for our discussion. There's our sugar compound. And, humans, fungi, animals, right? Sabotage the cat that I have at home, right? We all have aerobic respiration, and the process is we take the sugar, we combine it with the oxygen, and what do you think? Does everybody remember what comes out? Carbon dioxide, water, and of course, energy, life. Okay? So that's us. And we end up here, water, carbon dioxide, and how do we get back? Because if we didn't get back, we would just sort of use it all up, and that would be the end, right? Plants, exactly. So plants, beautiful synthesis, photosynthesis, takes carbon dioxide and water, and what does it add to it in order to go back? Because we've taken some energy out. Sunlight, exactly. And we go back again. So that's the simplest sort of way to think about how life has been able to keep going, how it's in terms of the earth and our environment. All right, so what about the physics behind energy? Let's just remind ourselves of some of the big ideas. And the first big picture idea of this, we've seen sort of this one circle of energy coming from the sunlight, getting stored in sugar by the plants, and we are able to extract some of that energy to live. It's this. Energy cannot be created or destroyed. And I'm sure you've all heard about it, but sometimes saying it in a different way can make it a little bit more deep and profound. And I guess here's a connection to the universe that you did mention earlier, so I didn't forget. Think about this. The exact amount of energy in the universe that the universe started out with is exactly the same as today, is exactly the same as 1 billion years from now. It's kind of an amazing thing to really think about, right? The energy, the amount of energy here is not changing. Everything, all the action is due to these facts about energy. There's different forms. Energy can be transformed from one type to the other. This, for example, is embodied in the first law of thermodynamics, and it can be transferred and moved around. So that's all the action. So we're not ever going to be talking about making new energy in the sense of creating energy out of nothing, and we're not going to be talking about using up energy in the sense of the physics ways of using up energy. What we're going to be talking about is energy of a useful type being available or not, or how to generate that energy of the useful type that we want or not in better ways. So it's maybe somewhat subtle, but I think it's just something good to keep in mind. Okay, so let's now do another whiteboard discussion. I want you to be thinking about, and just give me some ideas of types of energy, some energy transformations that you can think of, and then what's happening with our little prop that hopefully everybody got one of. Start off with types of energy, then some energy transformations. And then we'll use our little prop for the first time. So anybody, types of energy? Potential, I heard that. Good. Heat. Nuclear radiation. Okay, I'm gonna leave that sort of going in, I guess not all of it's electromagnetic, but okay. It can be other than just radiation. So for example, it could be if you have a nuclear isotope which decays into alpha, and the alpha has energy, right? Because it's moving, I would probably call that kinetic energy, but it's connected with the nuclear process, so I understand what you're talking about. Any others?
Internal energy.
Pardon?
Internal.
Internal? Okay, so we have ideas, right? There certainly are different types of energy out there. And how about energy transformations that you can imagine? Photosynthesis.
Fission.
Okay, so all of these are ways that energy can be changed from one form to the other. And so our little prop here, right? Let's now just, light it if you want and make me feel like a rock star. Woo! All right, no. If you can light it if you want, and you just imagine, all right, so what are the energy transformation going on with this? Chemical to heat, thermal, some radiation as well, right? Because I can see it. So there's actually quite a little bit of energy transformations going on in here. By the way, does anybody happen to know what kind of fuel's in the lighter here? Butane. Is butane a fossil fuel? Okay. All right. Oh, I should remember there's a weird spot here. All right, let's now apply our we're all thinking on the same stage here. Let's now apply our thinking about energy transformations to the water cycle, which you may hear a little bit more about from Professor Nagy a little bit. So just looking at this water cycle, right? This is ocean-land piece, for example. I put up here some types of energy using the terms that we would typically use in physics, right? Many of you have already given them to me. Kinetic energy, the energy of motion, potential energy or stored energy of various types, heat energy, electrical energy, radiation energy. So does anybody see any here and that you would want to just point out? Energy transformations going on? Transformation. So.
No, transpiration, so from the water inside the leaf to a gas.
Very good. Okay. Any others? Yes.
Potential to kinetic when rain precipitates.
Perfect. Yep. Any others?
Electromagnetic from the sun to thermal in the water to potential as it rises.
Fantastic. So any others?
Radiation from the sun.
Radiation from the sun. So it's everywhere, right? You start looking at it, you'll see them everywhere if you start thinking this way. You start looking up and like, oh my goodness, electrical, where did that come from? And now it's turning into light that we can see. So, the idea here is that our whole world is built up of energy transforming and moving into different parts. And thinking about it and sort of helping quantify that can be helpful and useful under many circumstances. Okay, so here's some other just examples, sort of a matrix kind of thing, which I don't know if physicists seem to like matrices for some reason. This is again taken from Vaclav Smil's book. It's a graphic, and it's a matrix of energy conversions. And the top row here is going to be from some particular type to another type, and then here would be, our quiz show kind of thing. What would the transformation be that you could think of? So it's kind of pushing our brains a little further. If you're going to go from electromagnetic to chemical, what would a transformation be that would do that? From electromagnetic to chemical. Photosynthesis, exactly. How about from thermal to chemical? Combustion. Or if you happen to use boiling. But the idea is the same, right? You can affect it. And you can imagine doing all kinds of things, right? But all kinds of types of energy from, to, and these are just sort of some of the main ones. And if you just sort of stare at this a little bit, and I'm going to give you a little bit of time to do that, can you imagine which ones here would have been most important for human history, most of human history? You spot any that sort of stand out to you? And let's talk about human history up until the last 100 years. Combustion. Everybody agree? It's probably the most. Okay, let's agree. All right, so I'll stop and think now, and then we're going to, wow, time goes faster. Energy comes in different forms. It's conserved. It can't be created or destroyed. It can be transformed from one to the other. We've seen sort of some circles in terms of, for example, the water cycle. Does this mean everything can just go on forever as it is now? What do you think? Pardon? Entropy. Somebody says entropy. Does entropy mean something to everybody? I see a few nods. Does it not mean something to anybody? Will somebody say not because I'm going to talk about it? All right. So the answer is no. And the reason for this comes from a profound feature of our universe in simpler words, and these are not precise at all yet. I'll try to make it slightly more precise as we move forward in the discussion. Energy in a closed system, energy always eventually goes from a more useful form to a less useful form. That's a simple way of saying it. I like to think of it even simpler. Nature has some direction to it in a very profound way. And the person here to help us understand this is not the amazing Spider-Man or Superman, although it kind of looks like it with the cape. Anybody know who this might be a representation of?
Prometheus.
Yes, Prometheus. Right. So we're going to have Prometheus help us out a little bit. Prometheus is bringing, not the wheel because it's already been used, what down to humans by the Greek mythological stories?
Fire.
Yes, fire, right? All right, fire. So Prometheus is bringing fire, and fire, I'm just sort of using that as a hook, generates heat energy, obviously from stored chemical energy, be it in wood, coal, oil, butane, released during combustion. I'm just curious, how long ago, what do you think, how long ago did humans learn to control fire? And yes, let's do that question first. How long ago do you think it was, roughly? A million years? 100,000? 10,000? Ah, good. We got nice scales of 10. Perfect. So you're thinking about it in the same way I am, which is orders of magnitude. So I think it's around the sort of 100,000 range, 200 to 400,000. Does that sounds about right? And just if you think about life for the early humans, what kind of things did it change? Why was fire so important? Food? Safety? Warmth? I mean, all the basic things that enable us to live without always just being at the mercy of the nature, right? So it's a big deal, and it's completely understandable why, right, Prometheus figures so prominently in Greek mythology. Okay, now let's tie this back to the direction of heat flow. Cold, iced tea outside on a hot summer day. Does the iced tea ever get colder? No, right? What direction is the heat flow? So you have to sort of connect the fact that putting heat energy in is what will raise the temperature, and then that helps you realize it's, I think I heard, right? Basically from the hot summer air to the cold iced tea, warming the tea. So there's a direction here. You think, yeah, that's just because I chose a hot day and cold iced tea. Let's switch it around. Hot cup of coffee outside on a cold winter day. Does the coffee ever get hotter? No, right? Think about the heat flow direction, and you'll find it actually is the same direction as the one example we just did. It's from the hot coffee to the cold winter day. Cooling coffee, melting any snow, touching the cup. And so this is sort of the first simplest experimental proof of this fact that nature has built into it a direction in connection with heat, and that direction is dictated by the temperature difference. We've all learned this, but again, if you're thinking about it in a slightly different way, it can be a useful exercise. It's always from hot to cold, always from high temperatures to low temperatures, never the other way around. Right? And so this is just illustrative of this fact that nature does indeed have a direction. This hasn't been exactly connected with this word entropy that was brought up before, but we'll mention that briefly in a moment. But these events that have a direction occur every day. Right? In fact, it's happening in some sense here too. As I burn this, if I think about entropy, as I burn this hydrocarbons, going in one direction, trying to get it back the other way is a very long, time-consuming process. That's absolutely non-trivial. So heat flows from hot temperature to a cold temperature, and never the other way around. That's the one example we just talked about. Here's another one. A closed system, the general movement of things is from order to disorder, and I completely believe this one. Right? My room always gets messier. It never cleans itself unless I put in energy. It's just sort of an everyday example of life. So we believe these just two observations reflect a deeper law of nature, and it has been known to be called now the second law of thermodynamics. And there's many different statements of it. I've chosen 3 here that I think capture some of the main physics ideas behind it. The first one we've said now for the 3rd time, right? Heat energy will never flow spontaneously on its own from a cold to a hot body. Here's the one that's really going to be relevant, and I'm going to talk a bit more about. You cannot construct an engine that does nothing but convert heat energy to useful work. Right? And the efficiency will depend on the temperature difference. And the third one, which I before, every isolated system becomes more disordered with time. So these ideas are all embodied in the second law of thermodynamics. I want us to look at point 2, right? And that is to sort of finish off our discussion about these this morning about some fundamental efficiency limits. Right? If we're going to try to extract some work from this burning, this heat energy. So heat again, just remind ourselves, it's the energy that flows from one object to another because of the difference in temperature. This took a long time for humans to figure this out. So I say it glibly, but there's actually many years, hundreds of years behind this of misthinking about it. Heat is energy in transit, and matter does not contain heat. So this is just an important physics, consequence, thing to keep in mind. So heat is energy moving energy. There's no heat in this thing by itself, but as soon as I light it, right, now I can have heat because energy is in motion. Okay, the fundamental limit, the best you can ever do to extract work from this heat energy, which is what humans have done, right? We've taken fire in various forms, and we've turned it into machines that turn things, be they early steam machines, be they a car engine now, be they coal-fired power plants, right? We have taken this heat energy and we have turned it into useful work. And of course, that's also why there was so much interest put into this, theoretically, right, in the 17, 1800s. There is indeed a fundamental efficiency limit for extracting work from heat energy. It's called the Carnot Efficiency. And if you've already seen it before, you'll know this. If not, here's what it is. Only got 2 variables in this formula. T hot minus T cold, or T hot, or 1 minus T cold over T hot, whichever your brain likes to think about easiest. If you turn it into percentage, this would be the maximum efficiency for extracting energy, converting energy from heat to work, mechanical energy. Right? Just as a note, the temperatures must be in Kelvin for this to work. Any ideas why?
It is an absolute zero.
Exactly. Kelvin is the only scale that has absolute 0 as 0. And so this is necessary out here. You can also use, by just staring at this, if I make T cold in this formula, or what would T cold have to be to always have an efficiency of 100%? 0, right? So if you could somehow get down to the absolute 0, that would then be 100% out. Question?
Could you use the Rankine cycle, which also has an absolute 0? Or Rankine temperature scale, rather?
In principle, the units cancel. Yes, the answer is yes. As long as you get absolute 0, 0 in the scale, the actual, because it's a ratio, it'll work. Right. So, you're right. It's not just must be Kelvin. Yeah, you got me. Most often it's thought about in Kelvin, at least by you. All right, so now let's just take that in mind, and let's now look at a simplified view of a coal-fired electric power plant. Right? Some of our power here may indeed be coming from coal plants somewhere in Illinois or surrounding states. Here's an example of one, the Kingston plant. Right? It generates 10 billion kilowatt hours a year. Right? Enough electricity to supply 700,000 homes. Okay, that doesn't really mean much to me. They're just big, huge numbers yet in my head, but fine. To meet this demand, Kingston burns about 14,000 tons of coal a day. That also doesn't mean anything to me. This helps me a little bit, an amount that would fill 140 railroad cars, which is still hard for me to think about. So one of the things I do, and maybe you would want to do as well, is when you get numbers like this, keep converting or thinking about it until it makes sense to you and it becomes real. So the only way this became real for me was when I thought, okay, 140 railroad cars a day, how many per hour? That sort of started to have a feeling. And then it's about 6 an hour or something like that. And so that to me started then becoming more real. Right? We're feeding into this plant 6 railroad cars an hour of coal in order to be able to extract the energy out of it. And so the question of how efficient it can be really, really matters. We're using tremendous amounts of chemical energy in our coal. We're trying to turn it into more useful energy, certainly for humans, the electrical energy. And what is the efficiency? Well, we just learned that there's a limit. And what do you think is the maximum efficiency possible, just with numbers, roughly?
20 or 30%.
20 or 30%. Now, do you think that that's the efficiency that they really are, or do you think that that's the theoretical maximum from physics? Because the interesting thing about the second law and the Carnot efficiency is that's such a theoretical maximum. Which one is the 20 or 30% thing? That's what they actually are? Okay. I think Professor Crabtree will talk a bit more about that when he wraps things up. Okay, what about the theoretical maximum? What, 60%? What kind of questions, what are you thinking of when you give me that number? What are the temperatures, exactly. So you have to go out and find out. You sort of already, this diagram, as complicated as this is, and all the inefficiencies, all the engineering, from the physics perspective with the second law, it's pretty straightforward. What is the maximum theoretical efficiency? We need the T hot. Oh, there's something red there. Yep, so there must be a T hot here. We need a T cold, the condenser, the cooling water. And if you go and look them up, and you find out the high pressure steam is around 540 degrees Celsius. And the cooling water is right around, sort of room temperature, 20 degrees. The Kelvin, if you want to use a Kelvin scale or a different scale, that's fine. And now you just do the math, right? T hot, 540, 273, 813. T cold, 20, 273 to turn it into Kelvin. So now they're both on absolute zero. Do your little bit of math. So no matter what we do, this is the theoretical maximum, and the actual is less. You already have ideas of what it is, and we'll hear more about this. Now, the cool thing about this is any kind of a thing that you can imagine that we have today that's extracting work from heat, you can use this same approach to get the maximum theoretical efficiency, no matter how complicated. The car engine is very complicated, right? All kinds of engineering. So here's just a single cylinder, right, in a piston in a car engine. Right? So you've got all that sort of interesting mechanics like a bicycle, of turning up and down motion into something that's going around in a circle. Right? And throughout all that complicated process, sort of pulling in this fuel-air mixture, compressing it, and then lighting it, you still end up having a hot and an exhaust. There's still both of these. And so the Carnot efficiency doesn't need to apply. And because you can burn gasoline at a slightly higher temperature, that means that bigger number minus basically air temperature ends up to be divided by a bigger number, gets closer to 100%. And so this happens to be the maximum of about 73%. Now, of course, it turns out that the actual value is much less for many reasons. Nuclear power. How do you think the efficiency of a typical nuclear power plant compares to a coal-fired power plant? From the second law perspective. Okay, higher. So what piece of here do you think is higher that is leading you to conclude that? I can just push a little bit. Pardon? Okay, so I agree that if indeed all of this piece is here, right, the steam pressure and all of this going to the turbines could be at a higher temperature, that the efficiency would be higher. But what do you think is setting that maximum temperature in the coal-fired plant for this 540 degrees Celsius?
Pressure vessel that the water's going to come through.
It's the engineering part. It's not about how hot you can burn the coal. The coal burns hotter than that 540 degrees Celsius. It's this piece up here, right? The T hot that you're extracting work from. So in fact, it's exactly the same to first order, right? Because all you've done is instead of burning something, right, from the chemical side, you're burning something from the nuclear side. And so yes, there's additional concerns you have for maybe the different temperatures involved here, but in terms of the Carnot efficiency, and we'll hear more about this one from Mr. Crabtree as well, it's going to be basically the same. Okay. So, last little bit here, kind of reminding ourselves of one of the limitations of this discussion. The Carnot efficiency limit is only for extracting work from heat. So don't forget about this. For example, what does the second law of thermodynamics say about the efficiency of a hydroelectric plant? What do you think? Absolutely nothing. All right? The issues are primarily engineering. What do you think it says about the efficiency of a photovoltaic solar panel? Are we extracting? So the question you always be asking yourself: are we extracting work from heat energy? So again, absolutely nothing. There's other physics at play. We're not extracting it from heat energy. We're extracting it from radiation, which is one of the ways that heat energy can be transferred. But okay, so the second law of Carnot efficiency is limited only to extracting useful work from a temperature difference, heat energy. But it's really important, right? Limitation in our current world. We operate almost entirely. I think Professor Crabtree was telling me it's on the order of 78 to 80%. Right, of our energy, the whole world is by from burning fossil fuels, and we're almost always, other than maybe heating our homes in winter, almost always extracting useful work from that burning in some kind of machine. And so that second law limit is something we're always going to be having to live with. And of course, there's the additional unintentional consequences, right, of this fossil fuel powered world. And I'm going to finish off here by doing a little experiment up front. And unlike most experiments where they always tell you don't try this at home, I would say you can try this at home with a caveat, just don't burn your fingers, okay? Just be careful. So here's a little demo here. talking about? Okay, so all I have here is a little glass jar. All I'm going to do is we're going to have a camera view. I'm going to put the glass jar upside down. I'm going to light the lighter. I'm going to hold one here. I'm going to hold the other one under this, and we're just going to see what happens. So that's going to be our little demo. All right, let's see if this is going to work here. So, okay, so everybody can see inside the glass jar, right? So I've left a little lip that I can kind of put this up in. So I'm going to light them both so you can see, you're going to see one in the jar, one out of the jar. And hopefully I won't burn my fingers, but if I do, I won't say anything because I don't want a 911 call. So you can see one of them is just sort of hiding up under the jar, one of them is next to it. You notice that the one under the jar, right, just the vision of it starts getting blurry. I can see it, but you can't. I'm starting to get some water vapor forming, and now the one under the jar goes out. And it's not just my finger got tired. I can light it again. The second I put it up under the jar, it goes out immediately. Why is that? Exactly. And although you can't all see it, there's a nice, beautiful coating in here of moisture. And so if we want to just have a little brief discussion on that. Okay, does anybody happen to know, you already told me that is butane in here, I agree. Does anybody happen to know the chemistry of butane? What is butane? Okay, what two elements does it have? It's carbon, hydrogen. Okay, so then it's just a question of what ratios. Anybody happen to remember? Does that sound about right? So if you're sort of done, I'm a physicist, not a chemist, but I like to try to pretend occasionally I can at least write a chemical thing, right? So there's our 4 carbons, C, 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 C. And if you imagine trying to put the 10 hydrogen atoms around them, right? Try to, let's see, a couple of them are going to have 3, right? A couple of them can have 2, and of course I've already drawn, so there's all my hydrogens. So that's at least sort of one structural form we can take. There's another one, but that's less relevant for us. Okay, so we've got C4H10. So when I put it under here, you all said I ran out of oxygen. So I know I'm adding oxygen. And you guess what it might be going to? Experimentally, you couldn't see it, but I could see it. I claim there's going to be some water vapor forming. What else do you think there might be? CO or CO2. Let's imagine it's a case where you have lots of oxygen. In that case, it typically goes to CO2. If you have oxygen, less oxygen in the atmosphere, indeed, you can make carbon monoxide. And now you can just, you can sort of look it up. I believe it's this on this side. And then if we're clever enough, we could figure out how many of them they go to here. Has to be 8 there because carbon is the only one here, right? Okay, so the point is, and this should also feel very familiar. I'm a human. I ate my candy bar this morning. Okay, I didn't have CH4. Right? I had another little element in my thing, my sugar. But I certainly took an oxygen. I did exactly the same thing. So certainly an unintended consequence of our burning fossil fuels is that it indeed gives off all kinds of things that we also give off and need to live as well. And there will likely be other consequences to that in general. We'll hear more about that in a minute. Imaging World History book again, he says the following. All of this is just an interlude. Unlike its predecessors, fossil fuel civilization cannot last thousands of years. Stores of fossil energies are finite, and even their most efficient use cannot prolong their exploitation beyond a half millennium or so. Indeed, the end of fossil fuel societies will come well before the actual physical exhaustion of coals and hydrocarbons. The rising costs and growing environmental burdens of fossil fuel use will force our descendants, actually us more than likely, not just our descendants, to turn to solar energy flows or develop new sources of energy. Okay, so with that, I will thank you very much for your attention, and we'll turn it over to Professor Nagy to take us from here. So thank you very much.